So this is a chance for some of the people that have posters. There are more posters than there are flash talks. And so for those that are giving flash talks, this is a chance for them to convince you to go to their poster and ask them questions. So the first person giving a poster or giving a flash talk today is Christina Medina Plaza. She's a project scientist in the Oberholster Lab, and she's going to be talking about investigation of accelerated red wine aging using microoxygenation in combination with barrel aging.
Thanks, Karen, for the introduction. So it is very well known that when we put a wine in a barrel, mouthfeel and aromas complexity increase, and the extraction of those compounds from the barrel into the wine, it actually follows a diffusion kinetic, which means that at the beginning, they're fast extracted until it reaches a plateau or an equilibrium in the concentration on the surface of the wood and the wine. So when that point is reached, the extraction rate decreases, and most of the processes that actually happen in the wine when it's being aged in a barrel are due to the oxygen intake through the staves. So we thought, what if we do microoxygenation in barrel? We give the wine a little bit of extra oxygen, and instead of having to wait a long, long period of time, we can shorten that and reach the same product. So for that, we made a red wine blend, and we barreled down in new American oak barrels and also in stainless steel vessels, just as a control to see what the micro-ox on its own was doing to our wine. Then we had 3 different treatments, so no microoxygenation that we hold for 12 months. Then we have 1 milligram per liter per month that we hold for 6 months, and then 2 milligrams per liter per month that we only hold for 3 months. So basically, we try to give the wine the same amount of oxygen at a different rates. And then for each condition, we did it on triplicate barrels just to take into account the variability of the barrel composition. So on those wines, we check dissolved oxygen and also free SO2 weekly. And then we check acetaldehyde every month. And then at the end of each treatment, we check the color of the wine. We analyze the phenolic profile. So what was the flavonthiols concentration, hydroxycinnamic acid, the anthocyanins, and also the flavonols. And we also check the polymeric pigments. We also did all this analysis in the initial wine before it was actually put into barrel. And we finally did a consumer study only in our barrel wines to see if the consumers would have a preference for one wine versus the other, or if they could actually distinguish or select any of those wines. So these are the results that we got. So basically, there was no difference on the dissolved oxygen of the time independent of the treatment, which means that the dosage that we were using was not overpowering the capacity of the wine to take that oxygen. The acetaldehyde levels, which can be an issue with micro-ox, the final levels for each treatment were the same and they were not significantly different, which means that they were achieved at different rates, but at the same level. Then with the time, of course, we saw monomeric anthocyanin decrease, and that was more impacted by the vessel and the time that we hold the wine more than the MOX treatment. I mean, like basically, most of the wines have, say, similar concentration of monomeric anthocyanins and also similar decrease on those monomeric anthocyanins. However, we saw a larger polymeric pigment formation, so more of that stable color in those wines that were under microoxygenation, independent whether they were in stainless steel versus barrel. When we combined all our chemical data and we did what we call principal component analysis, just to see the similarities among the wine, chemically, the wine that we aged only for 3 months in barrel using 2 milligram per liter per month of microoxygenation was the most similar to that one aged with no MOX for a full year in barrel, just chemically. And then when we present all the wines to the consumers, we found no preference among the treatments. The consumers didn't say, oh, we like the wine that you aged with no microoxygenation for a full year over the rest of the wines that you aged with microoxygenation. So this leads to my conclusion and the take-home message that basically micro-oz could be a good tool to shorten barrel aging, producing wines that consumers appreciate at the same level as the long-term aged wines. Thank you.
All right, so the next person speaking is Andrew Michailek. I think he just finished his master's thesis. Is that right? Yes. And he did that work in the Oberholster lab, and he's going to be talking about the investigation of the viticultural performance of 4 Vitis vinifera Petite Syrah clones and their respective wine characteristics. Like those cooking shows, and your time starts now.
Hey everyone, thank you, Karen. Like Karen said, I did my master's thesis in the Oberholster lab, where I compared 4 different Petite Syrah clones for their agronomic performance and their grape and wine characteristics. The vines used in this project are just down the road in the RMI, where around a decade ago, clones 1, 3, 4, and 5 were planted in a randomized block design, and it helped us, do this project. So our main research objective, obviously, is are there differences in clone? Very possible that there couldn't be. And secondly, if there are differences, can we characterize them? Because if we can produce this information, it could be helpful to producers to better select a clone so they meet their stylistic and wine production goals more efficiently. Petite Syrah is an important component of red wine in California, whether through blending or in a Petite Syrah varietal wine. It also accounts for around 4.5% of all red wine grape cultivars crushed in California by tonnage. So if we could produce some information that's helpful to producers, this could be there could be financial implications for the state's wine industry. So what did we do? We tried to leave no stone unturned. So we did a lot. So using those vines in the RMI, we evaluated the vines prior to harvest, the grapes after harvest, and then the wines made from those grapes. During the growing season, we checked vine nutrition at bloom through petiole sampling. We looked at water status throughout the growing season. We tracked veraison to see if one clone maybe had started earlier compared to the other ones and finished earlier. We looked at canopy density as a metric of vegetative vigor. And we also checked grape ripening parameters, Brix, pH, TA, the usual. And post-harvest, we looked at yield components and cluster condition. Did maybe one clone have more green clusters, more sunburnt clusters, et cetera? We looked at pruning weights, and we used that information to determine if there are differences in vine balance between vegetative vigor and fruitfulness. We also measured the phenolic profile and the aroma profile of both the grapes and the wines in the same way. Phenolic profile was done through Adams-Harbison assay and reverse phase HPLC, and aroma compounds were measured through headspace solid phase microextraction GCMS. In terms of the wine analysis, we looked at starting must chemistry, phenolic extraction during maceration, yada, yada, yada. Finished wine, there's a lot of stuff we measured, in addition to descriptive analysis of the wines by a trained sensory panel. So, were there any differences? There were, which is good. But these results were a little complex. Some differences were bigger and smaller than the other ones. Due to lack of time, I'm going to touch on just a few of them. In terms of starting must chemistry, clones 1 and 4 were harvested at higher levels of Brix, meaning that these clones could potentially be more early ripening, which could be helpful for producers if there's a wildfire threat, labor shortages, et cetera. Clone 5 had the highest level of malic acid, which was cool to see when we evaluated the aroma compounds in the wine. This clone had a more correlation with MLF-associated aroma compounds like ethyl lactate, which was cool to see. In terms of phenolic profiles of the grapes, clones 1 and 3 had higher levels of anthocyanins. Clone 3 had lower levels of flavin-threols, the constituents of tannins, excuse me. In terms of wine chemistry, clone 3 had the lowest alcohol. Clone 1 had the highest levels of flavin-threols, and in general, clone 1 seemed to be the most phenolic out of all of them. They were either intermediate or higher levels of phenolics. And finally, clone 4 was higher in levels of anthocyanins and flavonols, which was important for co-pigmentation in young wines. Like I said, this is a big generalization of the results that were found, and you can look at these findings in a lot of different perspectives. You know, if a producer wants to use Petite Sirah for adding color, you may be only concerned with anthocyanin content. So I invite you to come check out my poster number 8, during the poster session. I'd be happy to take your comments or questions. And thank you so much for your time.
All right, our next speaker is Nick Damon, and he was actually advertised by Andrew Macaron during Andrew's talk. Yeah, he's done his work in the Macaron lab, and he's going to be talking about using hyperspectral tools to track grapevine stress in the context of GrapeX.
Good morning, everyone. You'll have to forgive me, I'm not quite off script yet. So today I'll be briefly describing an evaluation of hyperspectral information to monitor stress in a California vineyard. So the purpose of this study was to scale up leaf level measurements of stress with remote sensing tools that are going to be less labor intensive and give a more complete sense of vineyard heterogeneity. So as Andrew mentioned, this is part of a larger project, GrapeX, which is a multidisciplinary effort to optimize remote sensing tools, such as satellites for irrigation management in several crops. And another purpose of this study was to maximize yield, quality, and uniformity in grapes. So my name is Nicholas Damon. I'm a second-year Viticulture Enology graduate student, and my plan after graduation is to work in eastern Spain during the harvest season. So let's get into this study. So the experimental vineyard was in Madera, California, which is outside Fresno. And while the GrapeX project collected data over several years, I'm just going to talk about data from 2018 today. So 4 blocks of the vineyard were irrigated, and essentially we irrigated the bottom 2 blocks normally, and the top 2 blocks are going to be stress treatments, and those are colored as in the photo above. And while we irrigated these treatments, we wanted to monitor the effect of those treatments with on-the-ground measurements of stress. So those included more conventional measures of stress, such as water potential, and we also took gas exchange and then hyperspectral measurements, which we'll talk about later. So these data were collected before, during, and after irrigation treatments, and we also captured some stress throughout the day. So we have a seasonal lens that we're looking at the data, as well as a diurnal picture. So here's a spectroradiometer on the left, and this is something that we use to measure leaf reflectance at each nanometer, so it gives us a very high spectral resolution of leaf status. So as an example, a stressed leaf may reflect more visible light or less near-infrared light when compared to a healthy leaf. And leaves from blocks that received different irrigation treatments, we expect to see slight changes in the reflectance pattern of these leaves. So in order to compare the leaves, we're going to take some of these reflectances at specific wavelengths and calculate hyperspectral vegetation indices. So in this study, we evaluated almost 100 hyperspectral vegetation indices. Andrew talked about just the sheer number of these that are out there in the market. And we're going to see, what are the differences between them? Are they all treated equally? And how are they reacting to water stress? So the first one we're going to look at is called the Simple Ratio Pigment Index, which I'll abbreviate as SRPI. And we can see here the Simple Ratio Pigment Index was originally designed to detect changes in leaf chlorophyll content. And as we tracked gas exchange throughout the day, the change in this index is pretty similar. So earlier in the day, there are larger differences between the irrigated blocks and the stress blocks, and we see that being picked up in the SRPI index as well. So these normally irrigated treatments are more likely to have their stomata open as compared to the water stress treatments, especially in the early day when the air is more saturated. And so we found that this is a better time to measure SRPI. And the second index we'll talk about is NDNI, and this has reflectances that look at bands where water is known to absorb. Unsurprisingly, when we plot this along with water potential throughout the day, we see that the best time to measure NDNI is actually later in the day, closer to 4 p.m., which matches our expectations from water potential as the day gets hotter and drier and the plants start to dry out. Water potentials become more distinct between the two treatments. So far these results are illustrating that hyperspectral vegetation indices can be powerful tools in vineyard management. However, we should consider that they may be sensitive earlier or later in the day and may not be as sensitive at 1 p.m. when a lot of these satellite overpasses are happening and vineyard managers are making these decisions. So as we choose to find a less labor-intensive and more representative way to measure stress, we want to think about the time of day that we're making those measurements. So if you have any questions, please visit me at poster 9, and thank you for your time.
All right, our next flash talk is from Miriam Kaltenbach, and she is in the Forrestal Lab, and she's going to be talking about a comparative study on physiological responses to drought in wild Vitis species.
Hello, everybody. My name is Miriam Kaltenbach, and I'm a master's student in the Forrestal Lab. And please bear with me, this is my first time presenting what I've done so far as my research. I'm originally from Germany, and I'm a viticulturist by training and did my undergrad in Viticulture Enology in Geisenheim and came as an exchange student to Davis, and I did like it a lot. So I wanted to join a lab and do research and start a master's degree here. And I'm working with Andrew McLaurone and Bev Forrestal on a comparative study on physiological and morphological responses to drought in wild Vitis species. And the ultimate research question we are interested in is whether species native to drier habitats exhibited superior physiological performance under drought stress. And just a quick background, as you all know, the rootstock is the link between the soil and the cyan on the crafted crop, as we have in grapevines. And however, about 90% of all the rootstocks are originating from 3 species and their sessions, which are Bellangeri, rupestris, and riparia. But there's a broader wild species, or there's so many more we could consider as well, given the fact I've had those little icons, which should symbolize climate change, which we've heard a lot about today already. So I'm not going to talk about that as well. But what we all know is that water is going to be a very critical factor in the future, and we have to find ways how we could save it. And one way to think about it is about how could we explore the genetic diversity even more with the wild species we have all over North America, which could be related to climates that are naturally having extreme temperatures or less water, that are we assume, or our idea was, that those species native to those drier habitats perform better under drought conditions. And the way we've done this, so we had actually 26 North American genotypes, but I'm only looking at 9 in my study because we have also not only physiological measurements, but also morphological ones, which is very exciting because that's not happened a lot yet, because we have X-ray images of plant tissue of 9, which I have listed up there, and we've 2 treatments. One is a control, which is a well-watered, and then the other one is a drought experiment, which we performed in a greenhouse. And we took those images, and that's what I've spent most of my time with, because I was training a module so I could use artificial intelligence to not have to do that all, because I wouldn't be graduating until 2025 if I would have to do that all by myself. And we can already see some super interesting results. We will have to look into them further because there's not much out yet as research done with that type of imaging and segmentation. But what we for sure see is that there is a difference between the drought treatment and the control. The control having always a higher biomass as well, not only in canopy, but also in the roots. And we see some differences among species, which then will be very interesting, because then we could decide, oh, okay, those perform well, so we could incorporate them into breeding. And I would invite you to come to my poster, which is poster 9, and I'm happy to answer some more questions or take your comments. Thank you for your time.
All right, our next talk is from Kayla Elmendorf. She is currently a master's student also in the Forrestal Lab. And she's going to be talking about morphophysiological effects of elevated ambient CO2 on Vitis vinifera, Cabernet Sauvignon, and Riesling vines in the vineyard FACE, which is Free Air Carbon Dioxide Enrichment Experiment.
Hi, everyone. How are you all doing? Okay, as Karen said, my name is Kayla Elmendorf, and I'm looking at the morphophysiological or morphology and physiology of elevated CO, so the effects of these two from elevated CO2 on Vitis vinifera, more specifically Cabernet Sauvignon and Riesling. This data comes from University of Geisenheim, where Miriam attended in Germany, as part of their Vineyard FACE experiment, which stands for Free Air Carbon Dioxide Enrichment. As I said, my name's Kayla. I'm technically a UC Davis alumna. I graduated last year from the undergraduate program, and now I'm completing my master's in Dr. Forrestal's lab and expect to graduate this June. I have some images of me and Miriam at University of Geisenheim visiting the site and doing some work in Oakville. At the bottom there, you can see more of the site at University of Geisenheim, and then I included some sensational article titles to show that carbon dioxide is, in fact, increasing in the atmosphere. When this experiment started in 2012, it was 400 ppm, and as of 2023, we already see it at 420, so it's increasing quickly. So what is morphology and physiology? Morphology is the structure of grapevines, so that's looking at total leaf area, leaf weights, stomatal density, stomatal length, and Miriam touched on this, but we have micro CT scans, which are basically X-ray scans, kind of like a CAT scan of a brain, but of leaves, and from these we can get total volume of various leaf tissues within the leaf and connect this to physiology, which includes more gas exchange measurements, which we did using Lycor 6800, various carbon-13 measurements, and this is more how the grapevine is functioning versus how it looks. And some preliminary results. So just like Miriam, I'm kind of in the thick of getting through a lot of these results, but we do see that from June to August, there's a decrease in overall photosynthesis and photosynthetic the capacity. Oh my gosh, if you can't tell, I'm very nervous. Especially in Riesling, the difference between elevated and ambient CO2, the elevated photosynthetic capacity is significantly decreased from in the elevated trial or treatment. So this suggests that Riesling is a much more plastic variety and is going to be more negatively affected from elevated CO2 in the environment. Another thing we saw was decreases in other gas exchange measurements and differences in stomatal density and length. Over the season, there was an increase in overall stomatal density, but a decrease in length, which gives us a net decrease in stomatal pore index, or SPI, which can be directly correlated with other gas exchange measurements that, for example, we took using Lycor. I'm excited to connect the micro-CT data to all of this and look at mesophyll conductance and other tissue volumes connected to gas exchange, but this is what I have so far. Thank you.
All right, our last flash talk, but certainly not least, we have Lixian Lim, and he is a member of the Oberholster Lab. He's a first-year PhD student, and he's going to be talking about understanding grape smoke exposure impact on wine from the perspective of wine experts and non-experts.
Thank you, Karen. Hi, everyone. I'm Lixian Lim. I'm originally from Singapore, and like Kayla, I'm also a UC Davis alum. I graduated in 2021 with a degree in food science, and then I joined the Oberholster Lab last year in fall. And my main research topic was understanding the smoke exposure impact on wine. And in this first study, I'm going to present to you on behalf of the co-authors on this is understanding grape smoke exposure impact on wine from the perspective of experts and non-experts. So we all know that smoke taint in wine has been a prevalent problem in the last many years, especially in the industry in the US. So basically, smoke is absorbed onto the grape skins, which are rapidly glycosylated when wildfires happen. The other issue we know is that there is both free and bound volatile phenols that are present in grapes naturally. The smoke taint character is usually characterized by a smoky campfire medicinal aroma, as well as having a retronasal aftertaste. So a lot of these smoke taint aromas are released through the fermentation, as well as aging procedures, as well as through enzymatics in the saliva when someone takes them. So one main issue that we have is that it is difficult to mimic smoke-tainted wines by spiking them with the smoke taint marker compounds due to the synergistic effects of a very complex wine matrix. And currently, anecdotal evidence has shown that only about 15 to 20% of the people out there are able to understand and distinguish what the retronasal and ashy characteristic of smoke taint is. Hence, we decided to do an experiment to kind of test all of this. So this was the experimental design. What we did is we took a single lot of grapes and we split them into two. For one lot of grapes, they were going to be our non-smoke taint control. For the other set of grapes, we are going to intentionally smoke them on drying tables. So we smoke them on drying tables for 4 hours using smoke generated from a Traeger smoker. And this was actually comparable to smoke impact in the vineyard done by previous studies. So both sets of wine underwent standard winemaking practices, and then we had two distinct wines made. One, the smoke taint sample, and one non-smoke taint sample. So we did descriptive analysis with both of these wines, along with some other wines, and we generated a list of sensory reference terms to describe these wines. Next step was to do consumer testing, and that was to find out the threshold as to where consumers could test them. So in order to do this, we serially diluted the wines between the smoke taint and non-smoke taint samples. And then that gave us 6 distinct wines. One non-smoke taint wine, as well as a dilution series ranging from 1.5% all the way to 25% of smoke-tainted wine in there. So we conducted this with 2 sets of consumers. One, what we'll call the experts, where it was mainly wine professionals, and the other one is non-experts, which is more generic consumers on people who are not in the wine industry, but take and consume wine regularly. So we asked a series of hedonic, just about right, check all that apply questions as well, and open comments on what they did think about the wine. So what we could do from the data of kata analysis is we could match the frequency of the kata terms used, and using factor analysis, we are able to do a projection onto a sensory map. In such way, we can have something called a correspondent analysis, which is similar to a principal component analysis. From here, you see 2 different correspondent analysis, non-expert as well as an expert. I'll first talk about the expert correspondent analysis. In this, we can see that there's a clear distinction between the wines based on the first principal component. And here we can see wines A and B being more red fruit driven, wines E, F, D, E, and F being more in the smoke direction. From our analysis on the overall liking, we could see that there were differences in liking starting from wine B and very large differences starting from wine C. This could show that experts could see the difference starting somewhere at 3% of smoke tint. Now, for the non-experts are generally confused in terms of the rating of the wines. They actually liked wines A, B, and C very similarly, and they did rate wine C to be more fruit as compared to wine B. They were able to tell differences between F and A, and based on our ratings on overall liking, there were almost no significant differences up to D. So there were significant differences between wines A and F. So that could show that non-experts actually could not really distinguish the wine. So where does this put us in terms of research? So non-experts are not the best people to be able to distinguish smoke tint per se, mainly because they do not know what they do. Hence, there is a lot more research that is going to be needed to be done to understand where the threshold determination and where they can start recognizing this smoke tint effect. So I'd like to thank the USDA as well as Jackson Family Wines for supporting this research, members of the Oberholster Lab. And if you'd like to know more, you can come to my poster number 14.